I better check the. Let's see.
I started reading The Stand this weekend.
Oh, really?
I haven't got too far into it because of homework and everything. That's the only thing I don't like about school.
Did you already have the book?
Mm-hmm. I have probably 2/3 of all of his books, so I'm trying to get them all.
Yeah.
So I told my husband and I were talking about downsizing,
Mm-hmm.
and I was like, I'll get rid of everything. I said, but I will not touch my Stephen King books, and I have a couple books that are in sets.
Mm-hmm.
And that have stuff that go with them, like I pre-ordered them and stuff came with them. I was like, I won't get rid of them. I was like, but I'll get rid of a lot of stuff. I said, but my books are one thing I will not. Like, I like my books.
He lives up there in, is it Maine or New Hampshire? Maine?
Maine. He lives up there with Tabitha, and we want to. Well, husband wants to go up there to fish, and I said, we can go up there and fish. I said, I want to go do the Stephen King tour. And you get to see his house and everything.
Yeah, he's got to watch himself when he's out there jogging. Run you off the road.
Yep.
Okay. Anything in particular that's giving you trouble? Feel comfortable with each of the gas laws, know what their names are, conditions required. Okay. Before and after sets, combined gas law, then what I call, I don't know if you call it a state function, but it's the ideal gas equation that you use. If you only know the conditions right now, you can use that one. This one right here. You don't have to know before and after to use that one. Just what are the conditions. But you do have to be careful with the units. Since the units here are that, you have to be sure all of your others match up with those units. Then you can use that equation. With the before and after equations, the only one you have to be careful with is temperature. It needs to be in Kelvin. But everything else.
Kelvin's the, when it's Celsius, you add 273 to it. And then Fahrenheit.
Oh, yeah, if you need to convert, I always remember it this way.
I like the Kelvin. I just like the sound of it, Kelvin.
And you don't even have to say degrees.
Just Kelvin.
Okay. So what else did we cover here?
We went over the laws and kinetic molecular theory of gas.
Kinetic molecular theory, okay.
And then gas stoichiometry.
Dalton's law of partial pressures. Got that one?
Mm-hmm.
Okay.
Boyle's law, Charles' law, Drew's law,
Mm-hmm.
ideal gas law, and Dalton's law.
Yeah. And then, let's see. How about I'd like to use the examples we've got in here for stoichiometry are everything's in the gas phase. You got copies of everything? Okay. it'd be good to use if I could pull out an equation that has stoichiometry with mixed phases. Let's see. Maybe I can think of one right off the top of my head. The only ones that are in the review document are all gases, like number 80 is the combustion of methane. 82 is nitrogen monoxide and hydrogen. Let's see. How about potassium chlorate, which is a solid. And then you heat it, and it decomposes. It's a decomposition reaction. And you get potassium chloride, which is also a solid, plus oxygen gas. Okay, so we just need to balance it. Let's see. Use a 3 here, a 2 here, and then a 2 here. That should be balanced. Okay? And you know, that's not a good choice because I can't use limiting reactants. I've only got one. Okay. Let's try this again. Okay. How about zinc, metal, plus hydrochloric acid yields it's going to be aqueous and hydrogen gas. There we go. Now we got solid, aqueous, and gas all together. Okay. So let's say we have. Let's start with the acid first. Let's make it fairly concentrated. Say it's 1.5 molar, and we have 2.3 liters of it. And let's say we have zinc. How about 25 grams? Okay, and we want to find out not just the moles of gas. Let's say we want the volume of hydrogen gas you got all your handouts you need? Yes. Okay. Have you had a chance to do the exam?
No, I was going to do it today.
You want a hard copy?
Yeah, that'd be fine.
Okay. Okay. So we want volume of hydrogen gas, only we need other conditions, right? Because with a gas, in order to define the conditions of a gas, you need pressure, temperature, volume, and moles. Okay. So let's say we're gonna have the temperature. Let's make it standard. No, for gases at 0 degrees. Sorry. 0 degrees C. So we've got temperature. Volume is going to be our question. Pressure What kind of pressure do we want? Let's say we're going to let it build up to 2.5 atmospheres in our container. And then moles is going to be determined by these conditions. Then we'll do volume. Okay. So moles is not given yet, but it will be. Okay. I'm just making this one up on the fly. This stoichiometry problem with gas involved. Okay. So first thing we do, limiting reactant. We got to be sure which one's going to run out. Right? Okay. And since we're headed for this one, when we do our calculations, we want to find out how much of that will each one produce. Okay. So if we say 25 grams of zinc, we need to know how many moles of zinc. So zinc is right here at 6538 per mole. So that gives us so many moles of zinc. Oops. So I get 0.3824 moles of zinc. Okay. And we need to know how many moles of this. How do we find the moles of our solution? How many moles of hydrochloric acid? Oh, wait a minute. Hold everything. Dick Tracy calling headquarters. You remember that cartoon? That's too old for me. It's not balanced, right? We got 2 hydrogens over there, so we need 2 here, right? So now we have 2 chlorines, and we need 2 chlorines here. When is that right? Let's see. Nope. That's not right either. Now it is. Now we have 2 chlorines, 2 hydrogens, 1 zinc. Now we're good to go, right? Okay. Okay, so we need to find out how many moles of this. So what's the definition of molarity? Moles per liter, right? So if we need moles, we just need molarity times volume. So these are in the right units, molarity in liters. So we just say that, and 1.5 times 2.3 should give us 3.45. 3.45 moles of HCl. Okay. So as we can figure it out now. We know which one's going to run out. Right? So if you take this one, we just jump through all the hoops. So that's moles of zinc, and we have moles of hydrogen. So we got 1 hydrogen, 1 zinc. It's going to be 0.3824 moles of hydrogen. Is what we're going to produce. And moles of HCl, this is 1 and this is 2. It'll just be half that. Right. 1.73. That means that this one's going to run out first. Right? That's our limiting reactant. That one right there. Okay. So now that we know how many moles of hydrogen we have, and we set the conditions at 0 degrees centigrade, 2.5 atmospheres, and now we know moles, we can calculate pressure. Volume. Because we got pressure. Yeah. So what formula do we use? Is this a before and after or a statement? Do we know before and after on this one? No, we only know what the conditions are right now. So we have to use this one. Right? And we want to know volume. So volume equals nRT over P. Let's see. Be sure. Still picking it up over there. Okay, so we know the number of moles. 3, 8, 2, 4 moles. We know R, 0.08206. And we know temperature, centigrade plus 273, right? The decay. And then pressure, which is 2.5 atmospheres. Now, all these units are correct because this one is liter atmospheres per mole K. So there's our K, there's our moles, there's our atmospheres, liters left over. Get value?
3.42 or 3.43.
343?
Mm-hmm. Sorry. I had to round it in my head because I lost my calculator.
Okay. So that, at this pressure, that's how many liters of hydrogen you'll have after this reaction. Now, if I'd had time to do this off camera, I'd have better numbers up here. And I might have even had you collect your hydrogen over water and use Dalton's partial pressures to subtract the water vapor out to find out what you actually had in hydrogen. In him. In order to use Dalton's law of partial pressures, I would have to give you a chart. And then the total pressure, well, actually, this problem is as is. Only if I told you what the pressure is over here, would you, and collect it over water, would I need to tell you what the temperature was, where you have the temperature, and then you could use that chart to tell you what the water vapor pressure was to subtract. So that would be a separate problem. This problem stands as it is. It's a stoichiometry using gas laws. And that's the type of problem that snuck through on the chapter right before this, right? One that I X'd out. That's the way you would solve that other problem. Probably ought to put that in the review document for future reference. We'll take a picture. I'll change some of the factors though, because I probably should have made these a little closer together, so you really have to work at it to figure out which one was eliminated. Let's see, there's my camera. I know it's going to be on this one, but I need a still shot. Let's see, that looks usable. While I was talking, did anybody think of a problem they might have? Anything giving you difficulty? How about, oh, anybody have trouble with 81? Using gas laws to determine a molecular formula. You know what that is?
Mm-hmm.
Might have to go back and review your notes, previous chapter. 15-gram sample of hydrocarbon is placed in a balloon at 1 atmosphere and 25 degrees centigrade. The volume of the balloon is 12.2 liters. Hydrocarbon is 79.89% carbon and 20.11% hydrogen by mass. Determine the molecular formula of the hydrocarbon. Okay. On its face, it looks really complicated. Unless you tear it down, break it down. Okay. If a problem is asking for, let's say 81. If the problem is asking for molecular weight, you're going to need to do two things. You've got to determine the empirical formula first. Then you can determine the molecular formula. So you're going to do this one first. Then you can do that one. And this one, you need two independent sources of information. The empirical formula you can do with percent composition. That's simple. But in order to go from empirical formula to molecular formula, you've got to know what the molar mass is. Right? What's the molecular weight? Okay. So we've got let's do the empirical formula. It says there are only two elements in here, carbon and hydrogen. So you've got carbon, hydrogen, and it says the carbon is 79.89%, and the hydrogen is 20.11%. Yeah, in this case, it tells you the mass of the sample. So we don't have to assume 100 grams. Right? It says there are 15 grams of sample. Actually, it doesn't matter. You can use either method, either the 15-gram sample or assume 100. So let's use the 15-gram sample. So if this is 79.89%, how much of that sample is carbon? 15 grams. And this means 0.7989 grams of carbon per gram sample. Right? How do I know that? I divided this number by 100. Right? So now, instead of 100 grams, it's 1 gram. So now these will cancel. And that will give us
11.9.
how much?
11.98.
11.98 grams of carbon in that sample. And we should do the same thing for hydrogen. Which would be 0.2011 grams of hydrogen. That's it.
3.01.
3.01,
Yeah, 165, so 0.02.
0.0165.
65.
That's good. Grams of hydrogen. Okay. Now, what's the next step? We've got to find the simplest whole number ratio. Those are not whole numbers, right? So the simplest thing to do is take the smallest one and divide everybody through by the same one, because this is the ratio. That many grams of carbon to this many grams of hydrogen is the ratio of carbon and hydrogen in the compound. So if we divide everything through by the same number, it's not going to change the ratio. This one's going to be 1, and this one's going to be 3.5, something like that.
Sorry, I was writing stuff down. I'm trying to write and do calculate at the same time. It didn't work out.
Well, we have to spread the joy around. Somebody else do the calculation.
Yeah, 3.97.
3.97. Okay. That's close enough to 4.
Yeah.
Right? So we're going to say that's 4, that's 1. So the empirical formula is 4 carbons. Is that right? 4 carbons. That this does not compute. Maybe I put the wrong. No, that's carbon. That's hydrogen by mass. What did I do wrong?
On the empirical formula on the sheet, it says 1 carbon to 3 hydrogens.
Okay, something's wrong.
You took for carbon 0.7989 times 15 grams.
Right.
It was 11.98.
Okay.
And then you divided it, you multiplied it by 1 mole over 12.01 grams.
Oh. Am I being stupid or what? Let's do that again. I'm having a bad day. No wonder we didn't work. I'm trying to ratio grams, not moles.
I think we missed this step.
Yeah, I missed a step. Okay. And all right, now we're going to convert to moles. So this one's divided by 1.01. It's 2.987 moles of hydrogen. And this one's 9.97. Zero. Guess we're placed in the wrong spot. Carbon. Okay, so that was close enough to 1, and this one's close enough to 3. So the empirical formula is 1 carbon and 3 hydrogens. Now, while we're here, let's just go ahead and figure the empirical weight of this formula, the formula weight here. Sometimes I say empirical weight. So that's 1 carbon and 3 hydrogens. 15.04 grams per mole. Okay, that's the first step. Now we need to figure out what is the molar mass. All right, what do we know so far? Let me move this over so I can expand. Here we go. What do we know so far? Remember, we need P, V, N, T. Do we know the pressure?
Yes.
1 atmosphere?
Mm-hmm.
Okay. So we got that one. How about volume?
12.2.
What is it? 12.2 liters?
12.2 liters.
Okay.
We know temperature too. It's 25 degrees.
Centigrade, so that's plus 273 equals 298. A. Okay. We've got all these conditions. We can find out how many moles is represented by 15 grams. Grams per mole is molar mass. So we just need to solve for moles. PV over RT. So pressure is 1 atmosphere. Volume is 12.2 liters. R is 08206. And temperature is 298. So the number of moles I got 0.4989. Am I the only one calculating? Okay. So the molar mass, the molecular weight is grams per mole. 15 grams divided by 0.4989 moles. Which is 30.06614.
0.6614.
How about that?
All that kind of stuff.
So what's the ratio here? 2 to 1, right? That means, where did I write the empirical formula? Oh, here it is. So that means the molecular weight is the the molecular formula is the empirical times our value of X, which is equal to 2. That means the formula is C2H6. And we would have got there 5 minutes faster if I hadn't screwed up. So really, the important thing, actually, the most important thing when you read a problem like this is, what's the question? The question is, what is that? Then you say to yourself, how do we get to that place? Think back to your composition, chapter on composition. Say, all right, you have to do the empirical formula first, then you have to get the molar mass, molecular weight, by some other independent means, ratio them, then you can find out what that X is. So then you break it down into those 2 parts. All right, do I have enough information to do the empirical formula? Yes, I do. So do that, get the empirical formula. Then do I have enough information to give me the molecular weight? Right? Well, the molecular weight is mass per mole, right? We got mass right here. How many moles does that mass represent? And then you look at your gas information. And it turns out, yeah, we got these 3. We and solve for that and using that formula. Pop's your uncle. So, logical approach takes a complex problem and breaks it down into little pieces.
What about 80?
Number 80, okay. Let's remove the evidence here. See what we got. How many moles of oxygen gas are needed to react completely with 51.2 liters of methane, CH4, at standard temperature and pressure to produce carbon dioxide and water, according to the following reaction? So you're given the balanced equation right off the bat.
Mm-hmm.
Standard temperature and pressure. Okay. That's the bad thing about grandfathering in standard temperature and pressures from history. Standard temperature and pressure for gas, standard temperature is 0 degrees centigrade.
Mm-hmm.
Standard temperature for everything else is 25 degrees. So we got to say, which one are we dealing with here? It looks like I assumed 0 degrees. So standard temperature and pressure here is 1 atmosphere. That's the same for everything for pressure. Temperature is 0 degrees centigrade. Okay. So everything revolves around this equation. CO2 and water. You know what? Okay, we're just going to have to take it at face value. At 0 degrees, water's going to be a liquid, isn't it?
Mm-hmm.
That probably wouldn't affect our calculations any. Because the question is asking for oxygen. Okay. So we'll just stick with the plan. That's 2. That's 2. So what are we getting? 51.2 liters. And the question is, how many moles of oxygen? So we need that value for oxygen. All right. So if we need to know moles of this, we can't find moles of that until we know moles of this, because this is the only thing that's given to us, right? So we got to find moles of that. That should do it. We know volume, we know pressure, we know our R, and we know temperature. So that'll give us moles of methane. Because the question was, how much oxygen is required to react completely with all of this? Right? So we're looking for the stoichiometric amount of oxygen.
just wanted to make sure I got the same thing you did on here. 2.285.
So that's how many moles of methane. Now it's conversion factor time. And so we have 1 here, 2 there, and 2 times that would be 4.570 moles of oxygen. I did that right.
4.57, yeah.
That's as far as you need to go. So puzzled. Is it okay?
Yeah, I just heard I saw where you got the 2 from.
Oh, yeah. Okay. S2019 caught my eye. Let's see if that was worth dealing with. A gaseous, 79. A gaseous compound containing carbon and hydrogen was analyzed and found it consists of between 80 and 90% carbon by mass. At 145 degrees Celsius and 1 atmosphere, the density of this compound is 2.45 grams per liter. A gaseous compound, that's important. It's a gaseous compound, has a density of 2.45 grams per liter, which is fairly tenuous, but normal for a gas. What's the molar mass of the compound? Okay. First of all, what's the question?
Molar mass of the compound.
Right. Question. Right, molar mass, molecular weight, the compound, which is a gas. Okay, then let's see what we have. What information are we given? We'll come back to the carbon part. The temperature, 145 degrees centigrade. Let's just add 273 to it. So that's 3, 4, 18. Yeah, 18. And we're also given pressure, 1 atmosphere. We're also given density, 2.45 grams per liter. And then we're told that the carbon, percent carbon is between 80 and 90%. Okay. So we're headed for molecular weight, right? Which is mass per mole. We have density here, which is mass per volume. And we've got some gas information, and that's important because this is a gas. So we're probably going to be interested in the gas equation. Now, if we want mass per mole, can we get mass per moles out of these others? Well, let's see. Let's change this to something a little more manageable. Use a little m for mass and a little n for moles. So the mass here corresponds, and moles here correspond. Okay. So how about this equation? We got temperature, don't know moles. Do we have volume? Well, volume is here, and pressure is there. Okay. So these three equations are related to one another. There, there, there. And the question is, what's the molecular weight? All right. So we want something that will have molecular weight on this side, everything else on that side, with these included, since we have information that will answer that question. Now, you could conceivably do 3 or 4 different calculations and start plugging them back in as you go. Let's see, how would we do that? Well, if we want this one, then we want to find mass and moles. Right? So moles probably would come from this one, and mass would come from this one as long as you know the volume, but we don't know the volume then. Right? We have volume in common here. So that probably would be a difficult endeavor, I assume. Let's see, did I miss something? 79, density, small mass. No, volume is not given directly. So let's say, let's solve this one for mass, since there's a term there. Right? So this one's going to be mass equals density times volume. Density times volume is mass. Okay? And this one, we need moles. So moles is equal to pressure times volume over gas constant times temperature. So if we substitute that one in here, right here, then we have pressure volume over RT. Okay. Now we have to go back to our math manipulations. So the denominator of the denominator, these right here, is the numerator. In other words, you flip it. So that means this one times this one times this one times that one over that one. Okay, I just took these two terms and they went up here. Okay, now we don't need to know the volume, do we? It cancels. So we have density, given density, R, we have temperature, pressure. Pressure. We're good. So now all we have to do is substitute our numbers. So density is 2.45 grams per liter, 0.08206, and times temperature at 418, and then divided by pressure at 1 atmosphere. Okay?
Got 84.
Okay. 84.04. Now let's see, what do we have here? This is liter atmospheres per mole K. So liters cancel. Grams is still there. Atmospheres cancel. And K cancel. So we still have moles. So we got the right units, 8404 grams per mole. Okay. Guess what? Blue smoke. You didn't even need to know that to solve the problem. That's the simplest way to solve it, by combining equations. I think you'd find out pretty quick that you couldn't do it step by step easily because you don't know the volume. If a volume had been given, then it would have been a bit easier to do it step by step. But since volume's not given, combining equations solves that problem for you. Volume cancels. That looks like a good bonus question here. Because that would take a while to ferret out the information. Time is precious on exams, I know. What if 80 to 90% carbon? No, it would have to tell you what the other elements were. Oh, it does. Contains carbon and hydrogen. 80 to 90% carbon.
So hydrogen would be 20 to 10 to 20%.
Right. 84 grams per mole. So hydrogen would be 10 to 20%. By mass. Okay. I'm not going to waste your time on that one. We probably could determine what the compound is. Right, but that's not the question, so we're going to let it go. My guess is that this problem manifests itself in other forms and could even be expanded into the question of what's the most likely compound. But I don't want to eat up all your time with something you're not going to need right away. Okay. What else? Under what conditions do real gases behave like ideal gases? That's number 78. Real gas approximates. That's a good word. Ideal gas at what? Temperature and pressure. High temperature, low pressure. Under those conditions, real gases can be treated like ideal gases. In other words, they don't deviate from the conditions laid out in the ideal gas equation. They will follow the ideal gas equation.
Maybe 77.
Oh, sure.
What was the answer to that one?
78 or 77?
Was that 75 yet up there? Or did I read
No,
it?
that was 78.
Okay.
That was A for 78. Low pressure, high temperature. Now we're going to look at 77. The largest party balloon can get before bursting is 8.55 liters at 25 degrees in 1 atmosphere. Suppose you fill the balloon only with oxygen gas How many grams of oxygen can be added to the balloon before it pops? Assume you have not yet added any gas to the balloon at all. So it's flat. Okay. Let's list what we know. Volume. Actually, this is maximum volume. So if we exceed that, the balloon pops. Equals 8.55. Better than that. Liters. Temperature, 25 degrees centigrade, which is 298 K. Pressure is 1 atmosphere. And how many grams of oxygen? So we're not told the moles, and we're not told the mass. But the mass, that's the prize. Right? But if we know this one, if we can find out this one, we can find out that one. Okay. So really we're aiming at this one first, then we'll do that one. And remember, oxygen gas is what? O2. It's a diatomic. If you forget that, you're proverbially screwed. Okay, I think we have enough information here to do ideal gas equation. Solve for moles, because that's what we want right here, so we can get this one. Equals PV over RT. So the pressure is 1 atmosphere. Volume, our target volume is that many liters, because if we exceed that, balloon will pop. And then the gas constant and temperature at 298. So we find out how many moles. So I get 3, 4, 9, 6 moles of oxygen. So now that we know the moles, we can convert it to, it's just unit conversion at this point. Right? The molar mass of oxygen is 32. So I get 11.2 grams of oxygen. Anything more than that will pop that balloon. Any others? About a concept question. 65. Let's see, gas in a container fitted with a piston has a temperature above 0 degrees. So if we have the temperature at the beginning, say initial temperature is greater than 0 degrees, then the Celsius temperature is doubled. So this is, let's say, this is Celsius temperature. And we're going to double the Celsius temperature is equal to twice the initial Celsius temperature. What happens to the volume? So we have the initial volume. Actually, what's the ratio, right? If we have the universal gas equation, PV over NT equals P2 V2 over N2 T2. Right? So the question refers to temperature and volume. Temperature and volume. These guys stay the same, right? So really we're interested in this one. Right. So if we change this temperature to that temperature, what happens to this one? Right. Now, this change, let's modify these so they'll be in uniform with our IDs here. Final. Okay, the volume, it doesn't matter what the units are. Temperature though, these temperatures are in K. So if we double the K temperature, we double the volume. But what happens to the volume if you double the Celsius temperature? Right? So there's the temperature, there's temperature. Well, we got an expression of volume over there. So what's the ratio of temperatures? Let's rearrange this equation so we get the final temperature in Kelvin ratio to the initial temperature. So now if the ratio here is 2, then the ratio over here would be 2. Right? So then I just move this one over here, move that one over there. Okay. So if we make the ratio, if we double this one, we have to double that one in K. But this is not K, this is Celsius. So what happens? Well, what is K equal to? Temperature K is this one plus 273, right? Okay. So let's substitute in here the Celsius temperature. Final plus 273 over, and then initial plus 273 equals, well, I already got there. Okay. Now, if we double this one to that one, then what we have is 2 times the initial plus 273 over the initial centigrade plus 273. Now I'm going to bring that other thing over here. So I have to keep pointing back at it. So this is the final relationship that we're talking about. So what's the ratio between these two? Well, you can pick a temperature, you know, something greater than 0. Right? Let's just say it's 10 degrees. Right? So if this is 10, that means this term would be 283. And if this is 10, that means 20 plus is 293. Right? So now the ratio of 293 to 283 is not double. Right? So this ratio, the volume will not double. It'll be, let's see what our choices are. What's true about the ratio of the final volume to the initial volume of gas? All right. It is 1 to 2. Final volume is 1 to 2. Well, you know, that's crazy because it's going to increase. 1 to 2 means it decreases. So D says it's 2 to 1. That would be the case if we had doubled the Kelvin temperature. But that doesn't even work. So it's 1 to 1. It didn't change. No, it's going to change, right? So A, C, and D are out. So what we have to do is say, which is it, B or E? The ratio is greater, it is greater than 2 to 1. No, can't be greater than 2 to 1, not even if this were a doubling of Kelvin. So the only one left is E. It's less than 2 to 1, right? It is going to increase, but it's not going to double. So it's less than 2 to 1. Okay. I took a long time to describe that, but the question was, what happens to this? And that depends on this. But the key is, these are Celsius temperatures. If you double Celsius, you're not doubling Kelvin. I wonder if there's a circumstance where if we double the Celsius, we would be doubling the Kelvin. Oh, it takes some algebra. I don't think we can. Even if we said this is 273 and that's 273, then that would be doubling 273. This wouldn't be doubled. Right? What if we took half of that? No, that still wouldn't work. Okay, so I can't envision a situation in which doubling the Celsius would also be translated into doubling the Kelvin. Just algebraically, it won't work. All right. Floor is open. Stop the band. Let's see if the thing pops out at me. Sometimes these concept questions give you trouble. They're just vague enough to mess with your brain. $63. Oops. Yeah, it was about to, needs to rest. Let's see, have a brand. Which of the following statements are true of real gases? Well, you can't pick more than one, right? Well, I guess we could. Did we do that in here already? Say, what type of reaction is this? And you could put more than one answer in the slot. Like, it could be in, did we do those in this case? Right. Oxidation reduction, maybe synthesis, that kind of thing. Okay. So I guess you could theoretically put more than one in here, but probably the best answer, there's just one of them that's not right, not true. That's worded wrong. No, it didn't, because there's only one true. Okay, never mind. Okay, 63. Which of the following is true? All right, so for A real gas behaves more like an ideal gas at high temperature and low pressure. A real gas behaves more like an ideal gas at high pressure and low temperature. That's false. It's just the opposite. Low pressure and high temperature makes a real gas behave like an ideal gas. Right? The particles collide with the walls of its container and exert pressure. Particles collide with walls due to pressure. Is that true? That's one of the postulates of the kinetic molecular theory. That's what causes pressure when particles are colliding with the walls. That's true. So if only one of them is true, you can stop there. We'll see what the others think. The individual gas particles have no volume. Is that true? No, they do have volume. They just have very small volume. Right. If it had said gas particles have very, very small volume in relation to the distance between them, that would be true. But as given, that's false. D, the individual gas particles are not attracted to one another. Gas particles not attracted. Is that true? Nope, they are attracted to one another. If they weren't attracted to one another, then you would not get condensation. Right? You know, cool it down, gas turns into a liquid. If they didn't attract one another, you could take that gas all the way down to nothing. That was false. And the kinetic energy of gas particles, kinetic energy of the gas particles is directly proportional to the temperature of the gas in degrees Celsius. Kinetic energy of the gas particles, directly proportional to the temperature of the gas. Directly proportional to the temperature in degrees C. Kinetic energy of the gas particles. Well, it's half right. Actually, it's not the kinetic energy of the gas particles, it's the average kinetic energy of the gas particles is proportional to the temperature. The individual gas particles have their own kinetic energy, and they will be spread out. Right? As the temperature increases, kinetic energy will increase. Well, actually, that's not true. Temperature which is proportional to kinetic energy on average. And this is the numbers of particles. They will be spread out like this in the proverbial bell curve. Right? So most of them will be, most of the number will be here, you know, at that. Well, and this temperature varies temperatures. So we're looking at the average temperature here for that group. So this is false with qualification. That wouldn't be a good test question because that E could be interpreted as true. So B and E could be true. So if that one shows up on the test, remind me. Reason I say that is this test has been in the box since the beginning of the semester. And I haven't looked at it recently, so I'm not sure what I put in it. Okay, any others? We'll see how we're doing on time. 9 minutes till 11. You got 30 minutes if you need it. That one's about to compile into 2. Yes. Yeah, you're good. And I'll post the video this afternoon.
So I can get a little bit that I missed.
Yeah, if there's anything significant, you see if it's there. Now, let's see. Did that one already. Oh, there's number 39 is the zinc, metal, and hydrochloric acid problem. Only this one doesn't give you the balanced equation. Yeah, you have to work it out. Okay. What's a torr?
760 tours of 1 atmosphere.
Yeah.
I'm remembering that as I keep doing them.
1 torr is 1 millimeter of mercury. They're equivalent. Just in case that one comes up and slaps you in the face.
Or 14.69 pounds per square.
Is 1 atmosphere. Yep. Right. All these are equivalent. Pound per square inch. And then we did the 760 torr and 760 millimeters of mercury. One other one. Inches.
Yeah.
2992 inches of mercury. Those are the only ones I remember.
Did you get the 101,325 pascals?
Pascals? No, I missed that one.
I have it written down because you said
101 something
101,325.
Pascal. Okay. And what's a Pascal?
Somewhere.
It's equal to a Newton per square meter. A Newton is a measure of force, right? And a Newton can be equated to using Newton's second law of motion. That force is equal to a kilogram times meters per second squared. Not that you need to know that.
Hey, here's one that's 32 pascals is equal to how many pascals?
232,
Yeah, and it says K. K and then P.
what number 31?
Yeah.
Let me see. Kilopascals?
Oh.
Yeah, that's what that means.
Okay, I was like, what in the world is that K?
I'm missing the value on mine.
It
What
puts
is it?
it all the way over here.
Oh, 232 kilopascals. Equals how many, what?
It just says equals Pascal, like equal
Oh.
blank Pascals.
Okay. So you just do this, and the third, and then resolve it. 2.32 times 10 to the fifth.
Yeah.
That's the way I do it.
Okay.
I just take the kilo, extract it out, slap it down there, and then resolve it into scientific notation. That's the same thing I do with,
It just caught me off guard because there was just a K and I was like, what's
yeah.
that?
You haven't seen that since first chapter, right? Trying not to go to sleep.
Yeah.
Well, I think we flogged this horse to death.
See y'all Thursday.
Okay. If this was general chemistry, we have a few other things we can talk about. But probably glad you're not in general chemistry. These way.
Yeah, my wife walked by the secretary, she looked in there, and she wrote me, she said, you need to wake up. She said, your head's about down on the paper. My bathtub pipe busted up before you talk. Somehow, man, I had a mess last night.
What pop?
Under my bathtub, the pipe that goes up to the nozzle,
Oh,
the hot water was busted.
yeah.
And it was like 10 o'clock before we found it. And I couldn't find the turnoff valve under the house. We was
Do you have a basement or a crawl space?
crawl space.
Oh, yuck.
So it's, I gotta go home and fix it too.
Yeah.
That won't be bad though.
Yeah, I mean, when you have a big rupture like that, it's easy to find the problem.
Yeah.
I got a slow leak in one of mine. I don't know where it is. Coming from my son's bathroom. Fortunately, our basement's not finished.
Yeah.
So I just let it drip until I can get around to it.
Yeah.
Are we good?
Going through some conversions.
Oh, okay.
You did need to know Pascal today. On 15 done conversions from pascals to atmospheres.
Atmospheres, okay.
I
That's
did
in,
it wrong at first, and it gave me a huge number, and I was like, that's wrong.
that's in useful information, I think.
I'm ready to go to bed. Worked all night.
Me too. I go home. I try to do work on the weekends, but I just get up late, eat breakfast, sit in my chair, and go to sleep again.
Fortunately, my son's grown, so I don't have to deal with kids.
Just 15 cats and 2 dogs. I guess those are kids.
Technically speaking.
So do we only have 2 more tests after we do this one next Thursday?
I believe so.
Don't we have 2 more and then
Fine. Yeah, we have this one and then chapter 16 and chapter 18 and then a final.
Cancel class
Oh,
today. Start checking Blackboard.
so we'll, I just started working on the final. The schedule says that I'm going to base the final on American Chemical Society sources, but I can't find any good ones. And I'm not a member anymore, so it's kind of hard to get at them. I used to be a member, but why am I paying, $120 a year and I'm there's nothing, getting nothing out of it. All they do is lobby Congress.
So our last day in here will be May 7th, pretty much.
Yeah, I haven't checked the schedule, the exam schedule to see if it jives with that. But what I usually do is, if your schedules, if we come to class at our regularly scheduled time during exam week and have the exam during that time period, does that conflict with any of your other classes that have exams? If it does, then I'll revert to their exam schedule. If it doesn't, we'll just stay our routine. All right, so let me know if your other classes want to hang with that exam schedule, and then we'll see if it conflicts with our regular time. Otherwise, might as well just come in when your biological clock says it's time to go to class. And they haven't